The solid line shows the standing wave pattern of a vibrating string which is fixed at ends x and y. The broken line shows the position of the string half a cycle later. The displacement at point Q is a maximum. So, here is our wave at this particular instant in time. Half of an oscillation later, it looks like this, and it's telling us that displacement at Q is a maximum. So basically, this is an antinode, and then what we see here, x, p, r, and y, those are all nodes. Okay, so let's go through the options. Option A, the distance from P to R is one wavelength. The distance from P to R is actually half of a wavelength. So one full wavelength, or one full wave, is this. That's one full oscillation, or one full wave. So one wavelength will be the distance from x to R. So P to R is actually half of a wavelength. So it's not A. Option B, a short time later the string at R will move up. At nodes, you have no displacement. So at points x, p, r, and y, you have no displacement, so R will not move up or down. It will just remain stationary, so it's not B. For option C, the lowest possible frequency for this string is 1/3 of its current value. That is correct. What we see here is the third harmonic. We can tell it's the third harmonic because we have 3 loops. Whenever you have a standing wave on a string, the number of loops tells you what harmonic it would be. So if you see 2 loops, it's the second harmonic, and so on. So this is the third harmonic. What third harmonic means is that the frequency of this harmonic, or of this oscillation, is 3 times the fundamental frequency, where the fundamental frequency is the lowest frequency oscillation. So when you have a standing wave on a string that just looks like this, that would represent the first harmonic, which is the lowest frequency oscillation. This, being the third harmonic, has 3 times that frequency. So it is C. Answer is C. I'll just go through D as well. The kinetic energy of the string has its maximum value. So the reason this is not true is because at the current instant in time, where the string is in this position, the velocity, the speed is 0. The string is momentarily not moving. It's reached its maximum displacement. When it does so, it pauses for a split second before it comes back down to equilibrium. So when the string is in this position here, or when the string is in this position here, it pauses for a split second before it comes back to equilibrium. And we can think about this in terms of energy conservation. So in the position that the string is in right now, it's the most stretched that it can be. And if it's the most stretched that it can be, it has the most elastic potential energy, and therefore will have the least kinetic energy.